Hey everyone, can I just please get a show of hands if you guys can hear me? Thank you very much. All right, good day everyone, and welcome to you all. And thank you again just for joining us. Before we begin, just a few housekeeping rules. If you could just please keep your microphones muted during the presentation. You are welcome to share your questions in the chat box, and we will be addressing those questions during the Q&A session, which will be held at the end of the presentation. And also please note that you will be getting a copy of these slides as well as the video recording a few days just after the presentation. You'll also be getting a certificate of attendance. We will be displaying a slide that has got a QR code which you can scan in order to get your certificate of attendance. This is again towards the end of the presentation. So it's a pleasure to welcome you again to our third webinar in this Power Systems series hosted by the Engineering College of Science and Technology. In our previous sessions, we started with the fundamentals of power systems, where we explored the core principles that underpin electricity networks. We then progressed into the integration of renewables into power systems, where we then examined how modern grids are evolving in response to sustainable energy demand. Today's session, we will take you through this conversation when we'll take this conversation a step further. As power systems become more complex, decentralized, and technology-driven, the need for advanced protection strategies and smart grid solutions becomes increasingly critical. Ensuring systems reliability, resilience, as well as efficiency in this new landscape requires not only strong foundational knowledge, but also an understanding of intelligent systems and modern protection techniques. My name is Cecilia Mateo, and I'm going to be your host for today's session. It is once again a pleasure to introduce you to your presenter, Mr. Samkelo Nene. Samkelo is a registered cannabis engineering technologist with EXA, and he holds a B.Eng honors in electrical power engineering. His strong academic foundation, combined with his growing industry experience, positions him well into the evolving field of power and energy systems. He has been recognized for both academic excellence and leadership, and continues to contribute to the advancement of sustainable and modern energy solutions through his professional engagement. As a lecturer here at the Engineering College of Science and Technology, he's passionate, about ensuring that complex engineering concepts are both accessible as well as applicable. Samkelo, over to you.
Good day, everyone. I hope I'm audible. And the slides are not moving from my side. I'm still on the cover slide. I'm not sure if it's my network or.
Okay, so I've moved the slides. Can you see the slides moving now?
Okay, let me take control.
So they're moving on our side.
They are moving.
Yeah. Perhaps log off really quickly and then just log on again, please.
Okay, let me do that.
All right, so let's just give Samkelo just a few minutes, please, to log back on. And then we'll just continue with the discussion once he's back on. In the meantime, you can just prepare your questions so that you can just insert them in the chat box easily and quickly once he's back and the discussion is already underway.
I am
Okay,
back.
see you still. Let's just try again. Okay, 1 second. Are you able to see the slides, Samkela?
I can see now.
All right, just please try and navigate.
So I've just stopped at the list of content. I'm not sure if everyone is seeing that as well.
On my side, it's still on the thank you slide. Um, okay, not yet. All right. If I move it on my side, are you able to see Samkela? I'm on the list of content. Thank you, Antonia. I'm gonna navigate. Can you see the next slide? Samkela, introduction.
So I'm still on the list of content.
Okay, no, it's fine. What we'll do is, Samkela, I'm gonna move the slides for you and let you know which slide I'm on, and then you can just present on it. Perhaps just open the presentation on your side. Is that okay?
Okay.
Okay, so we're on I'll go back to the table of contents, to the list of
Yes.
contents. You can just take us through, and then you'll let me know as we move through the slides.
Okay. So good day to everyone. Sorry about that. I hope everyone is good. We are continuing from power systems topic. Today, we will explore then the importance of protection in smart grids in modern power systems. And these are the content that we'll cover. It will be the intro, and then a brief recap of fundamentals of power system protection. Then we'll look into the adaptive protection strategy, and then also the smart grid technologies. We will also touch on the wide area monitoring systems, and then we will look at a case study then thereafter. So moving on to the next slide, to the introduction of importance of protection. Protection is the backbone of the power system. So in essence, if you think of protection for power system, what it does, it prevents damages to equipment and also ensures safety of the personnel that works on the power system, and also it maintains the system integrity. However, with the penetration of renewable, uh, your typical traditional schemes then find it difficult to ensure the safety and also to protect um, the equipment due to the fluctuation and also the intermittent power flows. Hence, then we need smart grid to provide intelligence in terms of managing the power flows through automation and communication. So we will move on to the next slide to touch on some of the fundamentals of power system protection. As I've said, that the main aim of power system protection is to prevent equipment damage, to ensure safety to the personnel working on the grid, and also to maintain the stability of the grid, as well maintain the integrity of the grid. So in essence, if you think of power system protection, what comes to mind? Anyone could pop a comment on the chat. There's also a diagram of a protective relay. What comes to mind when one thinks of power system protection will be the protective relay. Anything else or any component? Feel free to drop your comment on the chat. I may not be able to see the chat because I've opened my slides on using
No,
my
it's fine.
it's fine.
I'll let you know if there's anything. Yes.
Okay.
Okay.
So in essence, the fundamentals of power system protection relies on the send and isolate mechanism. If you were to think of a relay, that's what it does. Basically, it detects abnormalities, and then obviously then it will send an output, a trigger to the circuit breaker, then to break the circuit. So I hope we are all on the slide on the fundamentals of power system protection, where there is a drawing of the relay. As you see, there is an input of the current, voltage, insulation, temperature. And then obviously then the settings of the relay, your pickup levels, which will be your sort of like your threshold. And then also the time, which is the time for the relay to respond to the fault. So obviously then the settings, you have settings whether for current, if it's an overcurrent relay, or for voltage and so forth. And as long as the current or the input that the relay sees is is below the threshold, then it's in a normal state. Unless then it goes over, then the relay then has to send a command to the circuit breaker and break the circuit. So in essence, this is the foundation of the protection system for the power system. Going to the next slide, um, on traditional protection schemes. So what they use, we've already touched on the relays. They use relays to detect, and then obviously if there is a fault, then they send a command to the circuit breakers, as you see. Even though if you look at the picture of the circuit breaker, if anyone as well could pop a comment, what it reminds you of if you look at that picture of circuit breaker around your house that you have in your house, that you will be your DB board. If you were to look at your distribution board in your house, it's just made of circuit breakers. So and then on the far end you see the basic relay circuit. And another important component of the whole relay circuit is the current transformer, as you see there for CT. So we see at the bottom the incoming current. Uh, it comes, obviously it flows to the circuit, and then the current transformer, what it does, it will have a ratio of what, 1000 to 5 amps. It drops the voltage to a level where the relay is able to detect if there is an anomaly or not in the circuit. If there is no anomaly, then the relay operates as normal. It doesn't send a command. However, if it detects a spike in the incoming current, what it does then, the relay coil, I hope you see the picture, then is energized, which then close the relay contact as you see in the picture, and then the DC circuit with the battery then is energized, which then trips the coil for the circuit breaker, and then it breaks the circuit, and then the equipment then is protected. So in essence, that is the basic relay circuit, or how the relay then operates in conjunction with circuit breakers and the current transformers. So that's traditional protection scheme. And one of the important, hello, yes?
Sorry to interrupt. There is a question in the chat box. I don't know if you want to take it now. It's around the control circuit, or do you want to save it for later? Angela?
Okay, I'm opening the chat.
Okay, now it's what is the voltage to the vacuum circuit breaker? Do we have a main circuit and control circuit?
Yes, so let me go back to my slide because I was here now. So if you look at so the main circuit, as you see, is the whole thing, the outside here. And then the control circuit obviously is comprised of the relay coil, relay contacts, and then the trip circuit. So that is used then to control the circuit breaker, or rather to send command. So that's sort of like the control circuit. And then obviously the outside, or the incoming current, and also the current flowing past, or rather look at the bus bar rather as this whole picture, then is sort of like the main circuit. So this is in essence a basic relay circuit. There are no rating here in terms of current, no voltage. I hope that's answered. However, I will continue. If there are other questions, Busi, we will take them at the end, or when we are opening for Q&A.
Okay. Yeah.
So now we are on traditional protection schemes. So uh, coordination principles, it's very important. So the last time we did touch on zones of protection when it comes to the protection of the power system. Obviously, there'll be a protection for the generator. And as you see there at the top on either side, there are lines like sort of like squiggly. So that is a generator. And then obviously as you go down, then you see those circles, which are loads, which are connected to the bus that separate the loads from the generator. So what you normally have then is the zone of protections. You have a zone of protection for the generator, as you see the two circuit breakers on either side of the generator, and then you also have circuit breakers for the respective lines of the load as you see there. So that too will be a zone of protection for those lines. So for the first one, we see that there is a fault on the third load. If you were to obviously start from the left going to the right, you see that sort of like that yellow line like a lightning. It indicates there is a fault. So if there is a fault, it means there is a fault within that zone of protection of that line. Hence, then the circuit breaker that should trip should be the one in that zone, because then it acts as the primary circuit breaker. Whereas with the second or the second picture, the second diagram, you see that the main circuit breaker or the circuit breaker that's supposed to be, or rather that is within the protection zone of the generator trips. So that then is miscoordination because initially it's supposed to be the circuit breaker that's within the protection zone where the fault is occurring that's supposed to act first. If then it does not act, then the next circuit breaker then can trip. Hence, then, if you think of coordination principles, things like selectivity is very important. Selectivity, sensitivity, and also uh, stability as well. So your protection system should be able to be selective as to where the fault is occurring within its protection zone or outside its protection zone, and also speed as well is very important. Obviously, there'll be a time for the relay to respond. Normally, it's about, I think it's about 4 milliseconds, right? Or 400 milliseconds for the circuit breaker to respond to the fault. If it doesn't, then the next circuit breaker then can respond. So that in terms of the coordination principles. So coordinated protection is very important. As you see with the first one, it was successful, whereas the second one, it was not successful, even though one could say, however, the circuit breaker did act, the secondary circuit breaker. But let's say now for these three loads, we see that the fault is on the third load. However, it doesn't mean now we have to shut the whole thing, because if you look at where the trip is happening, it's happening at the generator, which is the main source of power. So in other words, now we're depriving these other two loads of power, even though the fault is not occurring on them. So it's very important to have a coordinated protection when it comes to the grid. And moving on to the next slide, this is basically on limitations of the conventional approaches. If you were to consider or think of your traditional relays, they're fixed parameter. So they're fixed parameters, which then are not able to adjust to dynamic conditions that are brought about by renewables. If you were to look at your traditional power system, whether it is supplied by coal or supplied by nuclear or gas, when it comes to then matching the load and the demand, sorry, the load and the supply, or the demand and the supply, uh, the transmission system operators, then they know that, for example, with synchronous generators, you are able to call them when you want them to come in. We touched on this on the last two webinars, that with your base load, you are able to bring them into the system when you require them. You are able to match the demand using coal and gas and nuclear. Whereas with renewable, you can't call them as you wish. You have to wait for them to be available. So with the conventional power system, you already know the power flows that will that will be flowing through the line before it even happens, because you know how much power you will call into the system. Whereas with the renewables, you have to it will depend on the obviously on the weather. It will depend on how they generate power. Hence, with fixed parameter, it becomes impossible then to detect any fault in the system. So this brings about complexity in the modern grid. And also, if you then use conventional approaches, they become ineffective because they are unable to respond to non-traditional conditions. And then this is why also modernization is important. Moving on to the next slide, we'll see. Please remind me if, because sometimes I might talk and not tell you that I've moved on. So I'm on modernization of the grid. There's a diagram that speaks about disruptive events, smart grid components. So this is why it's very important then to modernize the grid so that it has that flexibility and also is able to adapt to these dynamic changes. As we see that the smart grid obviously provides this adaptiveness and robustness, which leads to reliability of the grid. And also, if you were to think of restoration, the smart grid then is able, for example, if there is a fault, and then through automation isolation of the faulty section, is able then to bring your backup to help restore the grid. And all this together, restoration and reliability, then leads to the resilience of the grid. And moving on to the next section, which is on adaptive protection strategy. So we'll move on to the concept of the adaptive protection. So protection. So in essence, when you speak of adaptive protection, so we've covered traditional protection system where everything is sort of like fixed, is sort of like predetermined because we know how much power will be flowing, we know how much demand also will be getting. So it's easy to forecast a conventional grid. It's easy because you know how much people will be using. In the morning, in the evening, there will be high demand during the day, not so much demand, people at work. And then also we know that in the morning, perhaps we can sort of ramp up our peak power plants, our peak power plants, and then even later too as well. And then during the day, we can have our coal plant. Whereas now with renewable is something else. If you think of renewables, if you look at most curves of renewable, I think we had this in the last slide, in the last presentation, where we see the dark effect, where there is more generation during the day compared to in the morning and in the evening. Hence, it sort of opposes the demand. There's more demand in the morning and later. However, with renewable, there's more generation, and obviously we'll touch on this when we cover the energy storage technologies in the next webinar. So coming back to this concept of adaptive protection, so these schemes basically they dynamically adjust settings based on real-time system conditions. So they will use your digital relays, which then offers programming or programmable logic. So to be able to facilitate for this adjustment or this dynamic adjustment as compared to your traditional where it's just fixed. So again, they respond to load changes, renewable variability, and grid disturbances. So even our loads now is no longer fixed. Why is our load is no longer fixed? If anyone could comment on the chat, because even nowadays, uh, it's not just generation that is unpredictable, even our load as well. Why is that? Especially as those who are based in South Africa, we will know as to why, or we'll have an idea why even our loads now are also unpredictable. It's because people now they have rooftop solar plants, so they have second option. So then that also presents a challenge to our national grid operators or system operators when it comes to predicting our load, because people they have second options. So that also then will sort of have an effect on the load or the demand curve or forecasting. Going to the next slide. I've already touched on the digital relays. That's by using the digital relays, we're able to have this adjustment or to the dynamic condition, because obviously it offers programmable logic, and also it has faster response times as compared to your traditional relays, whether it is solid static relays or electromechanical relays. However, they are complex when it comes to, because obviously there's coding to it, and also they're expensive. And also another avenue can be a microprocessor-based devices, which sort of functions the same way as a digital relay, because it takes the analog input and then converts to digital processing or processor. It processes digitally, then sends out the output to the tripping device. And this is an example of an adaptive scheme. So if we move to the second slide, we'll see um, 3.3. The heading is 3.3.
There?
Yeah, you're there.
Yes.
Okay, thank you. So if you to look at then the two systems there, the first one is sort of a conventional distribution system where rather it's just one-way flow. If we say one way, as in like it's not bidirectional. So the power flows from the utility, from the generator, from the power plant to the load. So it's one way. So this is our typical distribution system. So as we see that, okay, the generator, which is then connected to the first bus, supplies the power, and then the line after the first bus, it has uh, circuit breaker, obviously the protection system for that line. And then after the second bus, there's another protection system. You can see each line has its respective protection system. Obviously, then if a fault occurs on either of the lines, then the protection system associated with that line will then respond. And then if you look at the second example, which is B, now we have bidirectional flow. If you look at after if you look after the second bus, we have distributed sources, which is our solar panel and also the wind. So we see there is a current coming from the utility, which is in red. There's also current going upstream. So we have current going downstream and current going upstream. So there is bidirectional flow. So a traditional relay wouldn't be able to pick up, or it might misoperate uh, or misidentify the current coming from the downstream. Hence, we need these adaptive relays that are able then to pick up that flow that is going upstream. And here's a quick question. Um, Imagine a wind or solar farm suddenly drops output. How should the relay respond then if it drops output? Anyone? Just a thought. Move on to the next slide. So now we will touch on the smart grid technologies. Again, as I've said, that smart grid technologies, they provide automation, communication, and intelligence to allow the system to adapt and also to self-heal and maintain a stability during dynamic conditions. So obviously a typical smart grid, the first layer as we see, I hope we are on that slide, number 4, where it shows the typical power system layout from generation to consumption. And then obviously then it shows the communication layer and then the application layer.
We are.
Moving on to, thank you. Moving on to the next slide. So when we defined the smart grid, we spoke about automation, communication, and intelligence. These are all, fancy words and all that. And sometimes they seems to be one thing. Anyone could quickly give us a difference between communication and automation on the chat. Feel free to do so. Again, here we see that on the on the first layer, we see your typical power system. And then on the second layer, we see control centers. So our control centers are our field devices. So these are our intelligent devices that give us analytics for predicting and also for adaptive maintenance. And then above we see communication. Obviously, the backbone of communication being your fiber optics, your Ethernet, and also wireless network, which then transfer or which helps to sort of transfer the data collected from by the sensors to the data centers or data hubs. Moving on to the next slide. So we see sensors, which are again, which are field devices. What then they do? Then they collect the faults, or rather they detect the fault, they collect data rather, and then obviously then that data, uh, the relay would detect the fault.
Sorry, Santila, are we on 4.2?
Yes, we are on 4.2. So we finished with 4.1.
Okay,
Are you there?
I'm there, yes.
Okay, thank you. So sensors are just collectors of data. That's what they do. By the way, we mustn't confuse them with the relay. So they collect data, and then obviously once the data is collected, then uh, the relays then will be able then using that data to detect whether there is a fault in the system or not. So this can be obviously done in real time to detect the fault, and obviously once the fault is detected with automation, then we are able to then seclude or isolate those faulty section. And once that is done, again, with the intelligence of the smart grid, then we are able, if for example there is a line that is faulty and we isolate that line, so the first thing it means that whatever power was transferred via that line or through that line is no longer transferred. So that might lead to a shortage in the supply, and then there'll be an increase in demand. We don't want that. We did touch on this on the last two webinars. There must always be a match between supply and demand, right? So if that line then is isolated, then the smart grid using its intelligent, obviously it will have to bring in your backup, whether it's peak plants or backup or storage to meet the demand. Hence, we call that self-healing in a way that the grid is self-healing, is able to then to adjust and match the demand with the supply. And going on to the next slide, are we there?
Yeah.
Thank you, Boosty. So this is also a component of the smart grid, integration of distributed energy resources and microgrids. Again, um, they help assist in terms of, for example, because distributed energy resources, it can be your rooftop, and also sometimes you might find that there is a wind farm that is connected at the distribution level, and then also your hydro pump storage or battery storage. So we call all of these distributed energy resources, as compared to, or rather, if you were to look your conventional energy resources, which is your power plant, which you'll find them that they're sort of like far, or they're a bit distance from transmission and distribution. These energy sources, they are closer to the consumers, and obviously they're everywhere. We connect them via distribution level or transmission level. They don't have to be connected to the generation network, as as we saw in the first webinar, where we spoke about generation, transmission, and distribution network. So These are also important part of the smart grid. They help, especially battery storage and hydro or pump hydro storage. Then they help in terms of energy management. Should there be a shortage, we don't then have to wait for plants to pick up. We can then use or dispatch these to help meet the demand at the distribution level. And then obviously microgrids are localized grids that can operate independently or in coordination with the main grid. Sometimes you might find that there is a fault perhaps with the main grid. So in order to protect the community, then you'll have a sort of like a microgrid, a small grid for the community. Then obviously then you protect it from whatever is happening in the main grid. And also if the microgrid, for example, a community or a state is unable to meet the demand, then you can um, sort of uh, get help from the main grid supply with the shortage. Going on to the next slide. So another part of smart grid is communication networks. We've already touched on communication, which is simply the exchange of data between utilities and consumers. Again, the backbone, communication networks, it's the backbone of that communication. Uh, again, as we said, through the use of fiber, Ethernet, wireless network, and also the Internet of Things devices, which help then to or rather enable this exchange of data between systems or between substation and from obviously from the field to the data controllers or data hub. And I think this is an interesting question as to which is more than it is critical, automation or communication. I did ask earlier the difference between automation and communication because they tend to sound the same. Which is more critical, automation or communication? Or rather, if I were to ask this differently, what is more critical is for the system to sort of respond on its own to the conditions, or it's for then the system to show visibility of what's happening in it. Which one is more critical for a smart grid success? I'll leave that to you. And then going to the next slide on wide area monitoring systems. So wide area monitoring systems, they sort of give an overview of what's happening in the entire grid, whether it's a grid of a country, and obviously, if you look at Europe, you have these interconnected grids across countries. So going on to the next slide, one of the important then components of the wide area uh, measurement system is the phasor measurement unit, which functions, which collect data as a center word. And then obviously this data that is collect, uh, whether it's voltage or current, it has a magnitude or angle. And then obviously then it sends to phasor data concentrator using your Ethernet. So your phasor data concentrator then becomes sort of like nodes where it aggregates all these measurements on the ground, and then it sends it to the data center or control center. And then the second part of it, going to the next slide, is the synchrophasors, which then, after the phasor measurement unit have then sent data to the phasor data concentrator, it then goes to the control center, where synchrophasors then provide visibility of this aggregation of waveforms, whether it's current or voltage of the whole grid. So then the operators then are able to see what's happening in different parts of the grid. So it provides visibility. So then they're able to pick up any transient, they're able to pick up any deviation in the frequency. just by having the visuals. Moving on to the next slide. So this is 5.3. Uh, this is a simply case study on the wide area management system deployment. So this deployment is in Great Britain, in the UK. I know you may ask as to why this one, why not maybe UK, why not South Africa, why not North America? So this one is different because it seeks then to address the penetration of renewable energy. So if you were to look at the grid of the Great Britain, it's sort of like synchronized isolated. Hence then the wide area management system deployment becomes critical to address some of the condition that then the grid may not be able to share with like the neighboring countries. As we have seen, I'm sure we have seen with the blackout that happened in Spain, Portugal, and France, where uh, the grid was the frequency was deviating, and France ended up cutting off Spain and Portugal because they had base load, which is nuclear, which is about 60% of their of their power supply or their energy uh, mix rather. They were able then to cut off Spain and Portugal, whose grid was highly penetrated with renewables. So if you look at then this case study of the UK being isolated, obviously, then they're able to sort of to actively manage the rapid changes that comes with the high penetration of renewables. And if we go to the next slide, uh, this is sort of like the breakdown or the infrastructure of the wide area management systems, where we see from the field devices where they have both the phasor measurement unit and also the waveform measurement unit. And then obviously then using Ethernet, your fiber optics, then they're able then to send this data to the data centers in the middle. And then obviously it then goes to the data hub or the national operators, system operators. And then going to the next slide, the future outlook. So in terms of the future outlook, one of the things that will be helpful or will sort of help in terms of grid resilient, it will be AI-driven protection. So that being adaptive. So obviously using analytics that are that are that are that are collected in real time, then to predict or forecast any fault that might occur. So if you were to think of predictive maintenance, so even in protection as well, then we'll sort of have this predictive protection where then we're able to predict when a fault is about to occur. And then blockchain enabled grid transaction is it's also one of the big things when you think of peer-to-peer transaction. So for example, if you have a rooftop solar, then you can, if you have a surplus, for example, during the day, then you can be able then to sell that power to the grid. So it's one of also the things that are in development. And also cybersecurity, which is also a big thing, remains a challenge in smart grids. And also in terms of people connected to the smart grid, you'll find that in most countries, even with smart meters, people are not or do not feel safe with smart meters. Some would even say that the government is spying on them. So that too remains a challenge in terms of how then do we protect the grid. And then obviously policy and regulatory frameworks. When you think of in terms of tax incentives, that supports the drive or the integration of renewable and the support the modernization as well. So that's all for today. And I'm happy today that we're able to make time for questions. So back to you, Busi.
Thank you very much, Samkela. All right, I am just going to check the question and answer chat and just check if there's any questions. Just please, again, audiences, please read your questions and just answer them in there. All right, so we've already handled the first one. I see, okay, I'm satisfied with the response that you gave. And then I think regarding your question earlier around automation and communication, someone said
Mm-hmm.
communication. So
Definitely,
that's it.
Antonio. I agree with you. Communication.
All right, I'm not getting any other questions. If there are, please insert them in the chat box. Questions, comments. I'm not seeing anything. I'm just gonna move through these slides so I can just get to the attendance, certificate of attendance slide. So, are the slides moving on your end? Okay, can you still hear me?
I can hear you. So I see thank you here.
Yes,
I
so
said,
yeah,
so are you
there
there?
is a
Thank you.
question. Yes, I am. Thank you. Yes, I'm at thank you. Sorry about that. There is a question. Antonio has posted a question in the chat box. It says, what protection is needed for soft start generators? For soft start generators implemented on an existing network.
Okay, software generators, Antonio. Perhaps I may ask software generators.
I guess there's sound. I think it's in response to your question. Okay.
Hmm?
Sound. I don't know if it's answering Antonio or adding to Antonio's question, but I've just received the chat that says sound. So again, the question from Antonio is, what protection is needed for the soft start generators implemented on an existing network? Antonio, can you just please expand?
Yeah,
I think
expand, yeah.
Samuel is just having yeah, difficulty understanding this question. And then Beke, what is sound, please? Or sound you can't hear us. Can everyone else hear us?
I
Maybe
can
that's
hear
what that
you.
means. Oh, okay. The sound from my system is not here. Can you guys hear me now? Okay. Samkela, there's another question. I wanted to know more about zones, but I cannot hear.
O-
Can you please just answer the ones around zones? I think maybe they're having trouble hearing me.
Okay. But Antonio, please do expand when you get time. So back about zones, zones of protection. So um in a grid, obviously you have a generator. Um I'm not sure, Busi, if you can go back to that slide. Let me I'll tell you which one. Or so zones of protection, it speaks about primary protection. So to be a protection for the generator, for the line, for the load. I
The
wanna go.
slide shows
Can you go back to the introduction? I think that's one. The first picture there on the introduction, number one. Introduction, importance of protection in smart grids.
all right,
That
I'm
one
there.
there. Yes. The one on the left. if you look at those dotted lines, you see there's one around the transformer, there's one around the feeder, the whole line. There's one around that generator zone. There's motor zone. So those are zone of protection. So each zone or each circles there will have then a protective system. So it will have a protective relay, a circuit breaker, which is supposed to respond when there is a fault within the respective zone of protection. So for example, if there is a fault in the transformer zone of protection, then the circuit breaker and the relay that is within the zone is supposed to act first as a primary protection. However, you'll find that if the system obviously is faulty, or if the protection is not well coordinated, you'll find that even though there is a fault in the transformer zone, perhaps a circuit breaker in the motor zone will respond. So that is miscoordination. So in essence, each and every zone has a primary protection system which is supposed to respond. If that doesn't respond after obviously the time based on the relay setting, then a secondary protection system, which is obviously in this instance will be perhaps the protection system of the feeder that will then respond at the secondary or backup protection system. So I'm not sure if that's clear.
I'm not seeing any responses here. Bigger, is that here? Are you answered? Right, while we wait for Bigger, I've also just asked Antonio to expand or just provide clarity on his question. I think we'll just give the question and answer session a minute, or just one more minute. Is there anything else that you would like to add, Sangela?
Not from my end.
All right. All right, I'm gonna move in. Are the slides moving on your end? I'm on the thank you slide right now.
Yeah.
All right. Thank you again, Sanjay. I think that was a very insightful presentation. And thanks again to our audience just for being patient with us and again just for engaging with the session. I'm going to display while I'm just doing thanks the certificate of attendance. If you may just please scan the QR code. There is also a link there that you can access all of this to make sure that you can access your certificate of attendance. And as you can see there, it says to receive your digital certificate of attendance for participating in the webinar, please fill out the form. This form, again, you can access it through the link that's provided or through the QR code. That is the only way that we're going to be able to get your information and the only way in which that we can generate your certificate of attendance. So please do complete the form online. And again, I think if today's events have been any indication of how resilient we are as engineers, so if you are interested in joining the problem-solving team, the adaptability team, please join ECST. We do have some events coming up. Our upcoming course, again, if you're interested in joining our campus, our college, we are offering a Bachelor of Engineering Technology in Electrical Engineering. Our intake is, our applications are currently open for intake for August 2026. So please go onto our website, complete the application form, show interest, and we will engage with you. Our program advisor will be in contact and just guide you through the entire process. With regards to upcoming events, we do have upcoming webinars. We have the ECST virtual information session that is taking place later today at 5 o'clock. So if you haven't registered for that, please do register. and join us later. Here you will find out information around the program offering and just a bit of an expansion around the college. So if you're interested or know anyone that might be interested, please join us. It's happening later today at 5 o'clock. We do have the energy, storage, and grid flexibility in modern power systems coming up. That's on the 1st of April. There's the fundamentals of electronic systems. That's on the 15th of April. And then there's the protection and reliability in electronic systems that's taking place on the 29th of April. Again, you can access the links via our website. Again, I think if you've registered for one of our webinars, you will get reminders for upcoming events. So just please be on the lookout for that. I think we have something, Samkelo, in the chat box just quickly before we log off. There is still 4 minutes. Douglas says, all right, there's quite a few. Let's just start again with Beke. He says, please explain the VT, which will give AC to the relay. Then why do we have DC that goes to the circuit breaker? And why also the relay is a protection relay AC or DC? I hope I delivered that one clearly.
So the DC power source, as we saw there, is for the control circuits, the inner circuits. So we'll see if you could go back there on the basic. It's 2.1.
So, 2.1, right? Um, second. All right, so I'm on 2.1, traditional protection schemes.
Yeah. No,
Yes, I
okay,
am on the slide.
the one before that one. Sorry. Yeah, that one
Traditional
there.
protection
Yes, thank you.
schemes.
The picture on the right.
Mhm.
So I would assume that it's about the tube circuit as to why it's DC. I would assume that that's what is asked, that's what the question is about. Then it's asking is the protection relay then AC or DC? What is it? Anyone feel free to comment on the chat. However, what I can say is that the battery then acts as a source for that inner circuit or for the control circuit as a separate source. Even though um, in terms of energizing the core, it's not necessarily the AC or DC, but it's the flow of current. So for example, starting with the current transformer, the incoming current, obviously if it's normal state, the transformer will then use the turns ratio 1000 to 5 amps, obviously to sort of drop it into a small current that the relay is able to sort of detect. If it's normal, then the current will flow as normal. However, if there is a sort of like a spike in the incoming current, the current transformer will then translate that to at a lower level that the transformer is able to detect, and then that flow of current then will energize that relay call, closing the circuit. Once the circuit is closed, we need the flow of current. Remember, the current that runs through the circuit breaker, it doesn't run through that relay contact and relay coil. It only energizes the coil. It doesn't jump to the control circuit. So the battery then is there to supply the current that is required to energize the trip coil.
Okay. Can we move from that one, Samkelo? Samkelo,
Yes?
are you done?
Yeah, I'm done.
Okay, thank you.
And
All
that's
right,
true
I
as well.
think
Just to comment on that class as well. Yes, they can be electromechanical units, obviously, which means they're using rotating part, or they can be digital, where they use electronic um, devices or components such as your triacs and your rectifiers. Whereas with electromechanical, they use contact, obviously to break the circuit. So you can continue, Busi.
Okay. No, I think that's time. We are on time today, so that is great, and we're able to cover a lot of questions. And I see there is comments. I will engage with these just after the presentation. Raj, just on your comment there around your online degree, our program is blended, but I think just join our session later on at 5 o'clock and just hear more about the program and hear about the benefits of a blended mode. And yeah, I think we can all learn a lot from that. Again, thank you everyone for joining and again for the engagement. We will see you in the next webinar. Thank you very much. Thank you, Samkela.
Thank you. Thank you everyone for joining. Take care. Bye.